Hello, my name is Joey and I'm one of the DB rethinkers at RethinkDB. Today I'm going to be giving a brief overview of our open source NoSQL software. I have open here two terminals, each SSH'd into a different machine. On the left is Newton and on the right Magneto. I want to start up an instance of RethinkDB on Newton, and because I already have the executable in my home directory, all I have to do is type in /RethinkDB and give it a port offset. Hit enter, and we can see here that the server is ready. The other important thing to note is the HTTP connection port is listed right here. Now we're going to hop over to our web browser and type in that port offset. We have here that the web UI opens up, and you can see that the initial page is the dashboard. It shows us that we are connected to the machine called Magnus, and will give us a general overview of our cluster. Currently, we don't have a lot running, so there's not a whole lot to see. The logical first step will be that we want to maybe create a table and insert some data. To do that, let's move to the Tables tab. You can see here that I already have a database called GitHub, but I'll come back to this in a few minutes. For now, we'd like to create a new table under our database test. One of the ways this can be done is to click Add Table, select the database test, and give the table a name. I'm going to call the table Dota, which is a favorite computer game around our office, and we're going to be inserting some data about a few of the characters. Click Add, and I can see that the table now shows up down here. In order to actually insert the data, we're going to move over to the Data Explorer tab. The Data Explorer uses our full JavaScript driver, but RethinkDB also supports drivers for both Python and Ruby. One of the cool things to note is that everything you see me type here today is actually fully executable JavaScript code. We chose to embed REQL into the host languages so that if you're an application developer, for instance, using JavaScript, you can write REQL queries and it feels as natural as possible. Of course, the same thing applies to both our Python and Ruby drivers. So starting off here, we're going to want to insert some data into our table. RethinkDB supports both single document inserts as well as multiple rows. Let's go ahead and see what that looks like. We'll start off with r.db test, and we want tables called Dota. We're going to want to insert first the name of, say, a hero, anti-mage, and give his role as carry. We can do a second one, let's say Chen, and give his role as a support. And then we're going to add on a .run. The .run is added at the end because RethinkDB queries are fundamentally chainable, and I have to tell the client when the query is finished and it can send it over to the server. This query gets compiled to an abstract syntax tree, and the entire query gets sent to the server for execution. None of it is executed on the client side. We decided to make our query language this way because we found things such as piping in the Unix shell to be extremely powerful as well as quite a bit of fun, and wanted to embed many of those characteristics into our language. The r dot I typed at the beginning is also there because RethinkDB language is inside a module, and we need to type r dot at the beginning in order to access the language. So let's go ahead and execute that insert. And if we want to now just look at our data, we can see, and actually hopping over to table view, we can see that we've got two rows, anti-mage and Chen, with their roles. Next, let's say we wanted to update some information in our table. And to do that, we could do, let's see, .get, and let's say Chen, and update his role to jungler. Execute. Let's take a look at our table. And you can see that now Chen's role has been updated. Now that we've seen the very basic get and set commands, we're going to explore formulating a more complicated query. To do so, let's hop over back to our Tables tab. Normally, I'd have an application sending information to the database, but since I don't currently have any application running, I've pre-imported some tables with data about GitHub. Here, I have a table called Repos, which contains information about the top 300 most watched repositories on GitHub. I also have a table called Events, which is a log of every activity in the month of October 2012 that occurred in these same repositories. Now, it might be a fair assumption that the most watched projects are also the most popular, and therefore should have the most commits. I'm hoping to find out which are the most watched repositories, how many commits each of them has made, and see if there's some sort of correlation between the two. Now let's go ahead and look at our two tables. If we want to look at table repos, we go db GitHub, table repos, and put on the .run. We can see here that table repos includes a ID, which is the name of the repository, as well as information about the number of forks and the number of watchers and the URL. If we want to see which repos are the most popular by number of watchers, we can add in .order by and sort in descending order the number of watchers. Many of the top watch repositories are things you might recognize, such as Bootstrap, jQuery, Rails, Homebrew, as well as a variety of others. Next, we're going to take a look at our events table. We do r.db GitHub again, table events, but we don't want to look at all events, we only want to look at commits. So we're going to do a filter where type is equal to push event, in this case meaning commit. And we will add our .run at the end once again. And here we go. The table events has information on the actor who made the particular commit, the timestamp, a randomly generated ID, as well as the name of the repository and the type. In order to figure out how many commits have been made to each repository, we're going to use a group by statement. We can do .group by, we want name, and we want to do a count of the number of rows that have that particular repository name. Group by is actually syntactic sugar for a grouped map reduce, which takes a grouping function, mapping function, and a reduction function. If we execute that, we now get a group and a reduction column. The group with the repository name and the reduction is the number of commits that have been made to that repository. Our next step will be to join this information with the information in our repos tables. Many NoSQL products don't support joins, but RethinkDB does. We're going to do an equajoin in this case, and we want to join our group with the primary key of our repos table, which is also the repository name. Lastly, we want to add a .zip at the end, which will make the output look a little nicer. Executing that, you can see that now all of the information we've had from our two tables is combined. The group and ID match up, and we have the rest of our information, forks, watchers, and number of commits all together. Finally, we'd like to do a .order by in order to figure out which repositories have the most number of commits. I want to order it in descending order and based on the reduction column. We then get the final output of our query, and not surprisingly, a few of the most watched repositories also had some of the highest number of commits in October. Also interesting is that there are a few lesser watched repositories, specifically XBMC and dot files, that had even more commits. Looking down the list a little further, we have repositories such as Git and, say, Linux that still had a pretty decent number of commits, but weren't nearly as high on the watchers list. Then again, every project here is among the top 300 most watched, so that's really not too bad. Now that we're done writing our query, let's see what it would look like to attach a second machine to the cluster. I'll go ahead and open up my terminal and start another instance of RethinkDB on the second machine. This will look very similar to starting the first instance. The only major difference is now I'm going to have to add in a -j command to tell it to join on the intercluster port specified over here. We can see that this machine is ready, and looking back at the UI, going to servers, we can see that a second machine has now been added to the cluster, this one called Viper. For right now, Viper has not been given any responsibilities and all of our primaries are still on Magnus. Next, we're going to shard our data in order to hopefully speed up our query, but we'd also like to make sure our data is replicated in case there's a server failure. To some, this may seem like a daunting task, but both can actually be done in literally a few simple clicks. If we move over to Tables and Events, scroll down to Shard Settings, we can change our shard settings to 2 and click Rebalance. We're also going to go to replication settings and change our number of replicas to 2 because we have 2 machines in our cluster. Similarly, let's go to table repos. Now, we don't need to shard table repos because it's a very small table with only about 300 documents, but we would like to back up this information. So once again, I'm going to set the number of replicas to 2. Now, moving back to our dashboard, you can see that I get a graph showing that the cluster is working to shard and back up my data. Under the hood, RethinkDB automatically balances the shards and assigns the primary responsibilities throughout the cluster. This process can take a few minutes, so I'm just going to sit here and wait. Now, I promise you, this is not one of those cooking shows where the cake goes into the oven and comes out magically frosted and looking perfect. I have literally been sitting here for about 3 minutes, and we can see from the graph that the cluster has just completed the sharding and replication process. Looking at servers, we can see that the responsibilities have been divided between the different machines. Magnus is given 2 primaries and 1 secondary, and Viper is 2 primaries and 2 secondaries. Moving back to the Data Explorer, let's rerun our final query from earlier. If we paste it in and execute, we can see that it actually does run faster. The same query has now been completely distributed throughout the cluster with absolutely no additional input from the programmer. Behind the scenes, the query gets compiled to a distributed and parallelized program that runs automatically on the server. This is the case for any queries you run, including the join we have here, any sort of multi-stage query, and even subqueries. So now that we've seen that sharding was successful, let's take a look at how the system handles a machine failure. If I go back to the terminal and kill Viper, we can see that I now have an unresolved issue warning. This is because Viper has become unreachable. To solve this, I either have to bring Viper back online or officially declare it dead. Declaring a server dead tells the rest of the cluster to take over its primary responsibilities and to ignore it if it comes back online, because at that point there may be data conflicts. Once the machine has been declared dead, though, I now have unsatisfiable goals. I must go ahead and change the replication settings back to 1 since I only have 1 machine available. I'll do this for the second table as well. Update. We see that all issues have been successfully resolved. Let's go and rerun our full query one last time. And look, it runs without any problems at all on the 1 remaining machine in our cluster. So, this concludes just about everything I wanted to cover in this demo today. We've looked at basic get and set queries in addition to creating a more complicated query of our own. We've also shown how easy it is to shard and replicate our data, as well as deal with simple failover scenarios. I encourage you to go to RethinkDB.com and download the product. Play around with it a little bit, and please come ask us any questions you have on any of the channels listed. Thank you for watching.